We have seen basics of probability in last few lectures. Today, our objective would be to learn a new topic, which is called conditional probability. The motivation for learning conditional probability is that sometimes the probability of an event, let's say A, once we know that it has occurred, might affect the probability of event B. Let's take an example to make this motivation clear. Suppose A is the event that one of your friend, say named Amit, is, and let's say the probability is 10% or something. It's a small chance. But let's say B is the event that Amit is in hospital. Now, if you know that event B has occurred, that Amit is in hospital, then you would assume that the probability of A given B must have increased. Our common sense tells us that this value should have increased. In other way, once we know that event B has happened, the probability of A changes and we want to capture this. This is captured as conditional probability. Probability of A conditioned on the event B. So let's formalize this. How should we define this? So let's say A and B are two events. We will draw the sample space as a rectangle. Let's say A is this event, B is this event. And these are different points in the sample space. Now, if someone asks us, what is the probability of B given A? Intuitively, if we know that A has occurred, then we should only care about this section. And then the favorable outcomes are this portion which is common between A and B. So it seems like that the probability should be the ratio of probability of B intersection A divided by probability of A. And this is how we define the conditional probability. So probability of B given A is defined as probability of B intersection A divided by probability of A. Remember that this is a definition. This is how we define conditional probability, which actually matches with the intuition as described by this photo. Let us take a small example to clear this. Suppose I ask you, what is the probability of two heads when I toss a coin twice, given that at least one coin toss is definitely heads? You might guess that it should increase. Let's find out clearly. The sample space has four elements: tail, tail, head, tail, tail, head, tail, tail. Once we know that at least one of the coin tosses head, call it event A, then the sample space is restricted. That means we only have to worry about head, tail, head, head, and tail, head. And the favorable outcome is this. So we see this is 1 by 3. Seems like three possible outcomes. One of them is favorable. Everything is uniform, so 1 by 3. But we can derive it using our formula. So probability of B given A, what is B here? We get 2 heads. So this should be equal to probability of B intersection A divided by probability of A, which is probability of B intersection A is 1 by 4 divided by 3 by 4. It makes sense. We can also use conditional probability to calculate probability of events by dividing the sample space in different cases. What do I mean by that? Let me start with an example and explain it to you. Suppose you have two machines, one is blue and the other one is red, and it churns out balls. Since you like color blue, let's say that you pick blue machine with twice as much probability as red. So you like blue, so probability of picking a blue machine is, let's say, this is 2 by 3, and probability of picking a red machine is 1 by 3. I'm making up events as I go. So AB is the event that I pick a blue machine, and AR is the event that I pick a red machine. Now, the blue machine gives defective balls with probability 1 by 4, and red machine gives defective balls with probability half. And the question is, you might guess it, if we pick a random ball, what is the probability that the ball is defective? There are clearly two cases, so we can just divide into two cases. One case is that we had used a blue machine. We know that the probability is 2 by 3. In this case, the probability the ball is defective is 1 by 4. So I get a defective ball with probability 1 by 6. For the red machine, I pick the red machine with probability 1 by 3. And once I pick a red machine, the probability that I get a defective ball is half. So again, with 1/6 probability, I get defective ball. So total probability of getting a defective ball is 1 by 6 plus 1 by 6 equal to 1 by 3. So you can make this calculation, but the question is, how did we come up with all these? Where did we add? Where did we multiply? Why did we do it? Say B is the event that ball is defective. So the formula we used here is that probability of B can be divided into two cases, and these are the all encompassing cases. Either I'm going to pick blue machine or red machine. There is no other case. So if I pick the blue machine, then the probability that the ball is defective is given by probability B conditioned, that's a blue machine, plus the other case where the machine I pick is red machine. In this case, the ball is defective with probability B conditioned on A. So you can see that this formula is used here to derive the answer 1/3. I can generalize it and say that if I have n cases or n events, A1 to An, remember that there should be disjoint events, important, and they should partition the sample space. That means they cover the entire sample space. There is no other point remaining. So if these two conditions are satisfied, very important, that probability of an event can be calculated by just going over all possible cases and calculating the conditional probability of an event given this cases. The proof of this is not very hard and is an exercise for you. Make sure that you do this exercise and you can derive this.